Okay, here the basic idea is to change coordinates from Cartesian to polar. Okay, so in the polar coordinates we have, so this is technically what we have. You have theta and r, and generally, not always, but generally r is given as a function of theta. And from here you have a map to the Cartesian coordinates x, y, and x is given as r cos theta, y is given as r sine theta. When something is difficult here and we suspect that it will be easier here, we pass it over here. But in practice, we superimpose these together only for these coordinates because it's easy to do that. So what happens is in one coordinate we see both of them. So for example here, when theta is constant, so suppose you take, okay, so this is theta equals theta 1. So you send it over here, you see that thetas are constant, so it becomes something like this. Okay, so we started from 0 here, so it goes like this. So it goes, if it goes like this, it is like this. Okay, so what else? If you say r is constant, okay, so if r is something like this, then it will be, again, we are starting with theta 0, so it will be something like this. Okay, so circle. Let me stop only over there. So if it goes like this, it will go like this. Okay, but we prefer to see both Cartesian and polar coordinates in one picture like this. So this is what we will do. We will change integrals to polar coordinates. From here, it follows that x squared plus y squared is equal to r squared. So this is the main thing that helps us in changing coordinates. So the important thing is here in the integral we have okay, here in double integrals we have dx dy. Here we have, here in double integral we have dr d theta. Okay, so the first temptation is to take this and replace it by this, but it doesn't work like that. Let us see why. Okay, so I have some pictures here. So let us again start from this picture here. In polar coordinates we have, okay, so theta r. So let us consider theta 1, theta 2, and r1, r2. Okay, so let us look at the area of this. Okay, area of this here. Okay, let's give a name to this. Call this region D. Okay, so area of D is equal to, well, from the figure we see that theta 2 minus theta 1 times r2 minus r1. Okay. Okay, so it's getting hot here, so I'll change. Okay, so let us send this region to the Cartesian coordinates and see what it looks like. Okay, so we are sending this over here with x equals r cos theta, y equals r sine theta, x, y coordinates. Okay, so this one goes to a ray, as we did there. This goes to the red ray here, and with this angle theta 1. Okay, so here this angle is theta 1, always oriented. Okay, the other one is another ray with larger angle. So here we have this thing. Okay, so this angle is theta 1, this angle is theta 2. Okay, so we are interested in this one. This is theta 2 minus theta 1. Okay, next we'll look at these parts, which was green over there. They go to circles with radius r1. So again, let's put r here to complete this. This is r. Okay. So this one is, let me extend this a little bit. Okay, so we have this R1 and then çok yaşa. And then we have this one R2. So this is the image of the region D. Let's call it D prime. Okay, so let's call it D prime. Okay, so what is area of D prime? So that was what we were interested in. Okay, so we remember the area of a circle, pi r square. The whole angle of the circle is 2 pi. So in order to find the area of a sector, you take the angle, divide it by 2, and multiply with the radius square. Okay? So the area of this is theta 2 minus theta 1 over 2 multiplied by the radius square. Radius is r2 square. From that we subtract the area of this sector, which is angle over 2 multiplied by radius square. Okay. So here I am using area of circular sector of angle alpha radius r is alpha over 2 r squared. Okay? And you check if alpha is 2 pi, you get pi r squared, the area of the full circle. So that's what we are doing. The angle is theta 2 minus theta 1 divided by 2. Then this pizza slice has area r2 squared times this. I subtract from this one, r1 squared. Okay, so it turned out to be a little different. If we want to write this as an integral, we will have from theta 1 to theta 2, from r1 to r2, dr d theta. Okay? If you evaluate this integral, you get this. But here, that's not what we are evaluating. This part is the same though, so I can write it as theta 2 minus theta 1 and take this 1 over 2 to the other side. R2 square minus R1 square over 2. If I want to write this as an integral, here you see that I'm integrating r with respect to r. It becomes r square over 2, and then I'm evaluating this. Okay, so it becomes, so this part is the same as here, the angle from theta 1 to theta 2, but this part from r1 to r2, I'm integrating r dr d theta. Okay, so you integrate this, you get 1 over 2 r squared. So maybe I do one more step here, theta from theta 1 to theta 2, and 1 over 2 r squared from r1 to r2, which is now equal to this. Okay, so this suggests that if I have the double integral over d prime dx dy, so this dx dy, this should be replaced by this. Okay, so this is one way of convincing us that dx dy is not immediately replaced by dr d theta. There is a correction factor. It has a technical name. It's called the absolute value of the Jacobian. Okay, because you can change, instead of sending it this way, you can change the order here. You should again get similar pictures. Then if you calculate the Jacobian, it will be minus r, but picture doesn't change. So you have to, when we are working with Riemannian integral, Riemann sums and other things, you have to take the absolute value here. This is also convincing because you see, if I take this sector closer here, it will be, the area will be small. As I go away, it will be large, and it is reflected here. If I take this figure here, if I move it down, obviously the area does not change here, but when I send it over here, the image will have a small area here. If I move it up again, the area in this coordinate system obviously remains the same, but when you move it over there, since r is large, the area will be enlarged, as we see in this picture. Okay, so this correction factor makes sense. Okay. Well, there is another way which we convince you about this correction factor. That's using a little bit cheating. I can derive that r as follows. So another way to see why dx dy is replaced by r dr d theta and not by dr d theta. We interpret this one. Okay, so what is this? You move x a little bit, you move y a little bit. The resulting area is dx dy. Okay, so now we'll do the same thing. We'll move r a little bit, we will move theta a little bit, so we'll get a picture like this, and we'll check what the area is. So this is again putting in onto xy plane the coordinates of r and theta. So suppose this is delta theta. So at this point, I have r here. Okay, so this is r, and this is here. This is theta. I move theta a little bit, d theta, and I also move r a little bit by dr, and see what additional area is introduced here. In this coordinate, this area is introduced. Okay, so read this as delta x times delta y. Okay, here what we cheat is we do this one. This is r plus delta r over 2, and here this is r minus delta r over 2. So this is the incremental area when theta is moved by delta theta and r is moved by delta r. Okay, so we want to find the area of this. So we'll again use this formula, which we have here. Okay, so the area is angle. So dA in polar coordinates is equal to this shaded area. Okay, so that's angle divided by 2 times this area minus this area. Okay, so this area is r plus delta r over 2 square r minus delta r over 2 square. Okay, so I expect this to be the area. Okay, so everything should work. So I have delta theta over 2 r square plus 2 times this r delta r plus delta r over 2 square here, okay, minus r square minus 2r, so I get plus r delta r. Okay, so 2's cancels, minus cancel, I get this. And minus square of this, delta r over 2 square. Okay? Okay, so these things cancel nicely. So this cancels, and you have 2 of these, okay? And you have over 2 here. So this gives you r delta theta. Okay, so in integration, this becomes r dr d theta. Okay, so dx dy is now replaced by this symbol. Okay, here you would ask why I cheated like this. Why didn't I add delta r directed to this? Okay, if I did this, if you follow the arguments, I'll have this plus, I think, delta r square times delta theta. So I will get a cubic in deltas, and I will try to convince you that when delta r and delta theta are very small, less than 1, then their cubic is negligible when compared to the square, which is correct. But in calculus, it is some of those negligible things add up to a very respectable value. So why doesn't it add up to respectable value here? I can't explain it. Actually, the explanation of this lies in differential geometry, exterior algebra, etc. Okay, there is a formal explanation of why, when you have delta r square, because one of them is delta r square, if you repeat something like this, it acts as 0, but that we don't do in calculus. Okay, so you have to read differential geometry books, which is generally done in third year. Okay, so those technicalities are not important for us. So we have 2 ways of convincing ourselves that incremental area element will have this correction factor. Okay, again, in this week or next week, we will have general change of coordinates, where we will show a more general way of calculating this. Okay, so polar coordinates is very visual, so we can convince you by drawing pictures that we have that correction factor. If you have a different set of equations here, there is a way to calculate the correction factor from here. We'll see that in this course, maybe next week. And then when we apply that technique here, we'll see that we'll get, again, r. Okay, so now that we have this, let us do some examples. Okay, so the next thing is, now we know how dx dy should be replaced. It should be replaced by this. In the formula of the function, you replace x by this, y by this. And of course, for this to be a reasonable replacement, after you do this, you should get a nice expression in r and theta. Otherwise, you solve it in xy. The important thing is, how do you find the limits of integration? Okay? If you consider this region, limits of integration is easy, because most of the time r is given as a function of t, so you integrate with respect to r first. Okay, a typical arrow parallel to this enters the region here, leaves the region here. You write those formulas. Okay, but we generally already have our figure in the xy plane. We don't want to take it over here and do the calculations here. We want to see everything here. A typical ray parallel to our axis becomes a ray through the origin. Okay, so in our region, we say consider a typical ray from the origin. When does it enter the region? When does it leave the region? Okay, so you write those things in terms of theta, of course. Okay, and then you check for which values of theta, for which interval of theta, your description is valid. Okay, so that's your double integral. So let me do that. Okay, so how to convert a double integral from Cartesian coordinates to polar coordinates. Okay, so we have this double integral d of f x y dx dy. Okay, so the first step is easy. Okay, as of course we want to calculate this, so it doesn't say just put x, y, r cos theta, etc. here and leave it as d. We want to calculate it so as iterated integrals. Because once we have iterated integrals, then we can calculate these things. Okay. So first of all, this part is, of course, trivial. And we also agreed that this one will be replaced by r dr d theta. Okay, so it comes this part. But we ask the same questions again. Okay, so we have, suppose we have a region like this. Of course, if you don't have a region like this, then you don't use polar coordinates. Okay, so this is your region D. Okay, so this angle is now theta 1. This angle is theta 2. You consider a typical ray through the origin. Okay, a generic ray. So it enters the region here when this is r is equal to, say, u of theta, and this curve is r equals v of theta. Okay? So then this is what you write here. First, we are integrating respect to r, so this starts from u of theta, it goes up to v of theta, and this description is valid from the figure from theta 1 to theta 2. Okay, so this obviously is very amenable to polar coordinates. Okay, so we have our region D in Cartesian coordinates, but the boundaries of it is nice so that we can express it in polar coordinates. Then this is how you pass to polar coordinates. If this part is difficult, then you don't do it in polar coordinates. Okay, so change of coordinates is always to make life easier. In the old days, we do this to make our life easier. Now, you try this, you give this integral to a software. If it doesn't do it, then you start changing coordinates, okay? Okay, so now I want to start with the examples. Okay, any questions so far? So everything looks easy. Okay, so let me start again with a very easy example. What could be the easiest functions here? Constants are always the easiest functions. So if you have here a circular arc, another circular arc, and if you are interested in the region in between, if you do this in Cartesian coordinates, you will always be dealing with square roots, and there will be several, at least two regions. In polar coordinates, you see it enters the region when r is equal to the radius of this part, leaves the region with the large radius. So let us do an example of that sort to get warmed up. Okay, so the region is something like this. Okay. What is the problem? Oh, the problem is to integrate. Okay, so this is the region. Let me make it look more realistic. So this is the region D. Okay, and the numbers are 1 and 2. Okay, so these are circles. Okay, so we are interested in, so D is the region in the first quadrant lying between the circles x squared plus y squared equals 2 equals 4 and x squared plus y squared equals 1. Okay, so far easy. No reason to pass to any other coordinates, but evaluate the integral. Let us give a name to this integral. D cosine x squared plus y squared dA. Okay, so you see that dA will be either dx dy or dy dx, but in either case, we don't have an elementary formula for the antiderivative of this with respect to x or with respect to y. So these are the cases where we are tempted to pass to polar coordinates. These x squared plus y squares do occur very frequently in engineering and science, and polar coordinates is one way to deal with them. Okay, so we pass to, so this is not possible. Possible to evaluate in xy coordinates. Okay, so when I say possible, let me put a filtration there. Okay, maybe you can invent some complicated formulas which will eventually give you the formula, the result. But at the level of calculus, we don't have a well-known function which is the antiderivative of cosine x squared plus y squared with respect to x. So we pass to polar coordinates. And then we follow this rule. Okay, so our integral I is going to be an iterated integral. Now I'll put x equals r cos theta equals y equals r sine theta, and it immediately becomes r squared here. This is cosine r squared. I'm replacing dA in Cartesian coordinates with dA in polar coordinates. In polar coordinates, dA is r d theta. Okay, so since this is the first example, let me mention that this is dA in polar. Okay, so already here we have hope to integrate this, okay, because now this is going to be, together with this r, we have an antiderivative sine r squared. Maybe we'll divide it by 2 or multiply by 2. We'll decide that later, but we have a nice function as an antiderivative. Okay, so the next thing is let's draw that red arrow. A typical arrow from the origin enters the region when r is equal to 1. Okay, very simple. That's why this is a simple example. Leaves the region when r is equal to 2. And when is this description valid? It starts from theta equals 0. So take this arrow here, theta equals 0. You go up to pi over 2. The same description holds. And after that, it's not our region anymore. So this is from 0 to pi over 2. Okay, so suddenly the integral becomes totally trivial. You see the limits of integration for r has nothing to do with theta. So actually I can see this as product of two integrals. This integral here, okay, so this integral here, oops, I have to take also dr. So this is one integral, there's no theta in it. So this is a constant. When I'm integrating with respect to theta, I can take it out the integral. Okay, so what happens is I integrate theta from 0 to pi over 2, and the constant is the integral of, okay, it has to be sine r squared. When I take the derivative of this, I'll have 2 here, which I don't have here, so I'll divide it by 2. Okay, so I check again. The integral is 2r over 2, so r, I have this, and integral of sine is cosine, so this works. Okay, so this is from 1 to 2. So now I have the integral. So this is pi over 2 times 1 over 2 times sine 4 minus sine 1. Okay, so let me see. Maybe sometimes I calculate these things. So this is minus, it turns out to be minus 1.59. So this is approximately, of course, minus 1.59. Okay, so this is the idea. What can be complicated? These regions can be complicated. Okay, so you may have some functions of theta here, so that after you evaluate this, now you have a new function of theta, and now you integrate that function of theta against theta. Okay, so that can be the only complication. Okay, let's go with some problems.
Can I add something?
Sure.
Isn't sine 4 bigger than sine 1? So how's the result minus?
Sine 4, sine 1 is, you see, sine 3.1 is pi. Okay, these are radians. Okay. So this is actually, this angle is, if you consider this, so I didn't check this, but this is probably what's happening. So probably sine 4 is this, so it is negative, and then sine 1 is negative, they add up. Okay, so let's also do one with the volumes, okay, and then we'll do other things. So let's do one with the volume. Okay, find the volume of the solid. So let me write the problem. Most of these problems I copied from the book. Some of them I invented because the previous problem suggests something. But this one I probably copied from the book. Find the volume of the solid bounded by the plane that is bounded by the plane z equals 0 and the parabolate z equals 1 minus x squared minus y squared. Okay, so we sketch the region in these things. So this is a parabolate. It's upside down because you see as x and y increases, this becomes first 0 and then it becomes negative. At the origin, this is the top of this is z equals 1, and then it goes down like this, up down to minus infinity. But we cut it at z equals 0. So here you have a bell-shaped figure. We want to calculate the volume of it. It has it has to be easy because here you have x squared plus y squared. So the domain of integration is going to be the unit circle, which we can parameterize in polar coordinates as r equals 1. So it will be easy. Okay, so the picture is something like this. Generally in these pictures, since drawing three-dimensional figures is not always very easy, we draw I try to draw this in the first octant. When x is equal to 0, I see where that parabolate intersects the yz plane. Okay, so that is z equals 1 minus y squared. So it is something like this, a parabola. Okay. When y is equal to 0, we have 1 here. Okay, so this is 1. And x equals 0, z equals 0, y is plus or minus 1 on both sides. So this is again 1. And here we have this circle, and this goes like this. Okay, so this is what you see if you look at this from the first octant. Okay, so volume is double integral over the region times height times dA in the region. That's always the formula. Our height is this one. Here, height is z equals 1 minus x squared minus y squared. Region is the intersection of this with this. Okay, so in the first octant, it's the unit circle. X squared plus y squared equals 1. I put z equals 0. And z equals 1 is in the xy plane. Okay. We look at the way x and y appears. It's all symmetric. So if I calculate the volume in the first octant and multiply it by 4, I'll obtain the volume. Okay. I don't have anything below the xy plane. So I have this one here. I have this one over there when x is negative, but this is positive. And I have in the other corner and in this corner. Okay. So this is equal to 4 times from symmetry. Integral. So I want to I want to write this in polar coordinates because this is a topic of polar coordinates. Okay, so height is 1 minus r square, r dr d theta, that's dA. In the region, r starts from 0, a typical ray like this starts from 0. So when r is equal to 0, the ray is already in the region. R starts from 0 and leaves the region when r is equal to 1. And this thing is valid when theta is 0 up to pi over 2, because that's all of my picture. 0 to pi over 2. Okay, so you see, this is what we are integrating, what we are doing in the polar coordinates. Okay, before we integrate this, let us do this also in Cartesian coordinates. Again, 4 times. Height is 1 minus x squared minus y squared. Let's say dx dy. This one is, you see, either it is r equals 1 or it is x squared plus y squared equals 1. So here, observe that I'm using r squared equals 1. I'm integrating with respect to x first. So if I consider an arrow parallel to x-axis, it enters the region when x is equal to 0, leaves the region at the square root 1 minus y squared. Okay, so this is where you get square root, and this is valid when this tip of the arrow moves from here to here, so from 0 to 1. Okay, so this is not an impossible integral, but you will have some problems here, because when you integrate this, here you will have x cubed. So when you substitute, you will have 1 square root here. And here, this is constant, but you'll have x here. That x will bring you another square root. So in the next step, you will need to put trigonometric substitution or do some integration by parts in this part maybe. Okay, so you have some extra work there, but it's not impossible. It's just a little bit more work than here. Here you see it is easy. This is 4 times integral. Well, actually, I can immediately evaluate this because the integral with respect to r has nothing to do with theta. So this thing is theta from 0 to, just to demonstrate this, from 0 to pi over 2. Here I have r integrated, so this is 1 over 2 r squared minus r cubed 1 over 4 r4 from 0 to 1. Okay? I take the derivative of this, I get r, I have r there. The derivative of this is r minus r cubed, and I have minus r cubed here. So I integrate this from 0 to 1. You see, this one was easier. So here I have 2 pi. Here I have 1 over 2 minus 1 over 4. So this is what? 1 over 4. 1 over 4 is pi over 2. Okay? If the answer is pi over 2, you don't check it in calculus. It's probably correct. Okay, any questions? So this part we only did as a demonstration. Okay. Okay, let's do one with the cardioid. Area of the cardioid is very popular with polar coordinates because that's also well motivated. If you want to calculate the area of it in Cartesian coordinates, you are in real trouble. Because by the time you manage to pass from polar coordinates to Cartesian coordinates in the expression of a cardioid, you have lots of higher powers. And then it's not easy to solve this. So, area of a cardioid of the form r equals 1 plus cosine theta. Okay, here theta is between 0 and 2 pi. The picture is something like this. Okay, so let's exaggerate and make it look like a heart, but if you draw this, it doesn't look like this. It looks much like a circle here, and you just have maybe some circular arcs. None of this is circular, but the actual picture is not beautiful. You caricaturize it a little bit. Now it looks like a heart. Okay, so we want to find the area of this. First of all, the area is symmetric, so I'll just write the area for the upper half plane multiplied by 2. Okay, so area 2 times integral. Okay, so you integrate 1 to find the area. 1 times dA. dA is r dr d theta. So let me again remind that this is dA in polar. Okay, so now we take a typical ray from the origin. When r is equal to 0, we are already in the region. And it leaves the region when r is equal 1 plus cosine theta. Okay, so 1 plus cosine theta. And this description for the upper half plane is true from 0 to pi. Okay, so this is what we will evaluate. So this is 2 times from, now I don't do this integration immediately because there is theta here, from 0 to pi. I have 1 over 2 r square from 0 to 1 plus cosine theta d theta. Okay, let us immediately cancel these. Now what do we have? Integral from 0 to pi. Square of this, 1 plus 2 cosine theta plus cosine square. For cosine square, we generally write 1 plus cosine 2 theta over 2. That's cosine square minus sine square. Yeah, it should work. Okay. So I integrate this with respect to theta. Okay. You see now everything is integrable in terms of elementary functions. So here I have 1 plus 1 over 2. So this is 3 over 2. 3 over 2. I integrate with respect to theta. Plus, so this antiderivative of this 2 sine theta. So take the derivative of this, you get this. And I have here cosine 2 theta over 2. Okay, so first of all, it must be sine 2 theta. If I take the derivative of this, I get 2 theta. I get 2 here, but I only have 1 over 2 here, so maybe I should multiply it by 1 over 4. Let me try again. Derivative of sine is cosine. Derivative of this is 2. 2 over 4 is 1 over 2. Okay, so I managed to have everything. So from 0 to pi. From 0 to pi. Okay. Now, nice thing about sine is sine pi is 0, sine 0 is 0. Sine 2 pi is 0, sine 0 is 0. So these parts do not contribute. So I could have written something wrong. I could have got the coefficients wrong, but as long as I got these sine theta, sine 2 theta correct, the answer would be correct. So the only thing is here I have 3 pi over 2 because theta 0 is 0. So this is 3 pi over 2. Okay, so let me see if that's what I found at home. Okay, so 3 pi over 2. Okay, so for the last problem for this hour, next hour I'll solve more problems. Let's look at, let us intersect this with the unit circle. You see, this is 2, this side is 2, this side is 1. So most of the time you intersect this with the unit circle here. Okay, so you have to find the area here and the area here, but that's easy. So maybe I'll leave it as an exercise. What's a little bit more challenging is put a circle here, okay, and then find the area of the intersection or area that lies outside. So let me draw the picture of this, and maybe after we draw the picture we can take a break and continue in detail after this. Okay, so I'll call this problem 3 prime. So we have r equals 1 plus cosine theta. So the picture is again something like this. Okay. X, y. So let me make this a little bit above here. And here I want to put a circle centered here. Okay, so this is 1. So consider this circle. Okay, so this is circle. So what is, okay, what's the formula for that circle? I'll write it over here. In polar coordinates. Okay, so first of all, it must have something to do with sine, because when theta is equal to 0, we have 0 here, and then it starts to increase. Okay, and when we come here, it is 2. Because if this is the center, when it comes here, it must be 2. So r equals 2 sine theta will probably be correct. Okay, so r equals 2 sine theta. So this part is 2, this part is 2, this is 1. So what is this point of intersection? So here you see we have several regions to calculate, several regions of interest. What is the area of this region? That's one thing. Once we find this, then the area of this region is from the area of this circle, you subtract this. Or we can look at the area of this, because that's again something we didn't calculate. Here I can use this. Okay, so those two regions are the crucial areas, because this part is easy. If I know this, I know this part. Okay, so the other part. So let's make this look like more like a circle here. Okay, so let's take a break while you find this point of intersection.